Hello everyone, this is Chris Surface here with the SDI course FTT 122 week 6 assignment. Today's date is March 16th, 2025. The first thing we're going to go over is trajectory and sights. Here I have a drawing on a dry erase board going with a couple demonstrations. Here we have a rifle with the line of sight coming from the scope to the target. Then the black line here is the trajectory. When a projectile is fired, it continues in an upward motion due to the positioning of the barrel. There it goes up until factors take effect and affect the actual trajectory itself. The two places where the trajectory crosses the line of sight are called point zero. You have one here, not too far past the muzzle, and you have the other one at the actual target. The other drawing I have here is a pistol. Since it has a shorter distance the projectile travels, there's only 1.0 for the line of sight and trajectory, and it's at the target itself. The next thing we're going to cover is gyroscopic drift. So as the projectile is fired from the muzzle, the rifling in there causes it to twist. While it's twisting, the gyroscopic drift tends to make it go the way the rifling twist is. So in this case, it would be clockwise, causing it to slightly drift off to the right. The third thing we're going over is drag. So when the projectile is fired, the nose here is pushed against air. Air is considered a fluid. So as its fluid is hitting on here, it is creating drag and creating pressure against the actual projectile, causing it to slow down and be affected. The fourth one we're covering is the Magnus effect. When the projectile is spinning through the air, if the wind comes from the spinning clockwise, if the wind comes from the left side to the right side, it will have an effect on the tip, causing it to dip downward, causing it to drop faster. Now, if the wind is blowing from the right to the left, it will cause the tip to lift and cause gravity to have less of an effect on the bullet. Next, we have the Coriolis and Eötvös effects. I'm going to use this kickball here and the projectile to kind of show what happens. So here we have this line we're going to use as the equator. The Coriolis effect is when it affects it from when it's shot perpendicular to the Earth's rotation. As the projectile is fired, the Earth spins, which causes the round to be off. If you're in the northern hemisphere, it will push the projectile to the right, while if you're in the southern hemisphere, it pushes the projectile to the left. Now the Eötvös effect, Eötvös effect impacts it on the vertical plane. So if you're closer to the equator, as the projectile goes around with the Earth curvature, the target's constantly moving closer or further away, which in turn will cause the bullet to either be higher or lower on the target. Now, the further you get away from the equator, the less effect it'll actually have on the projectile. Next, we'll cover vertical angles. This is shooting uphill or downhill. On here, I have a drawing. It shows you got your line of sight distance, your trajectory, your distance at which gravity affects the projectile, and the rise in elevation. I did some numbers on here. So the actual line of sight is 78 feet, where the rise is 50 feet, and the distance in which the gravity affects is only 60 feet. So there's a difference of 18 feet between the actual distance the bullet travels and how much gravity actually affects it. To figure this out, you can use the Pythagorean theorem, which is a squared plus b squared equals c squared. Lastly, we will talk about transonic ballistics performance. So this is where the round drops in velocity from supersonic down to subsonic. This is where the center of balance shifts and it causes the projectile to wobble. At this point, if it does not stabilize back out, it will be far off target. But a good projectile that is stable, a properly stabilized projectile, will actually come out of that wobble and begin to restabilize on its way to its intended target.